So the next big part of chapter 9 is going to be vectors, and we're going to review vectors first and then start digging into the calculus behind it. So a vector, as you guys learned it in accelerated geometry and pre-calc honors, as well as in physics, is a line segment with direction, and it's used to represent common things such as force, velocity, and acceleration that you find in physics, or you see it also in describing wind direction. And it involves two main things, magnitude and direction. So let's first start off with taking a look at if we had two coordinate points and connected it and labeled it, we would say that the first point that you guys see there, x1, y1, p, is what we call the initial point of our vector. So this is the initial point, and it's pointing towards Q with the arrow tip at Q. That is called our terminal point. The notation for vectors is usually represented in textbooks as PQ and then with an arrow or half of an arrow on top of it. So let me zoom in so you guys can see. But you would only draw a part of the arrow tip as the notation. So initial point first, terminal point after, with that arrow notation above it. Or sometimes, just like with lines in geometry, you see a single letter, common to call it vector V. Or V, if the V is written somewhere between P and Q, we can also say that that's another way of naming a vector. Scalars are quantities that represent, so it's usually like a constant value that represents magnitude, but it doesn't have any direction tied to it. So the notation for vectors, again, are highlighted below here. And one of the things you guys learned in geometry is how to find the magnitude or the length of a vector. So when I'm taking a look at how I would find the length of a line segment, we're going to think of what we did with arc length, and we built a triangle from it, for which we did Pythagorean theorem. Or where did Pythagorean theorem lead us to? It led us to distance formula. So the magnitude of a vector can be found usually with the notation. If you see the double absolute value bars, this is magnitude. That's notation for magnitude, and it can be found by the distance formula if we had the coordinate points x2 minus x1 change in x squared plus change in y squared. If you guys didn't have the coordinate points, and we'll talk about it when it's not in provided to us the vectors as coordinate points, what we would do if that was the case. But I want you guys always to think back to Pythagorean theorem, building a triangle from it and finding the length of that segment, or in other words, this vector. Vectors are equal if both their major properties are equal to each other. So if they have the same magnitude and if they had the same direction, we would say that they are equal to each other. A lot of the times the coordinate points aren't efficient in describing the vector. What happens is if a vector, and you don't have to draw this out, but I'll sketch a XY coordinate plane here. And let's say we had a vector over in the first quadrant, a vector over in the fourth quadrant, the second quadrant over here. And let's say that, I know it's not drawn to scale, but let's say these are all equal to each other. And each one of the initial points were given and each one of the terminal points were given. It would take a bit of work for us to decide whether or not the vectors are equal to each other. So it's convenient if they were all repositioned such that they were in standard position. Meaning if I were to pick up each one of these vectors and then realign it so that the initial point is on the origin, so each one of these initial points get moved to the origin, we would say that that new vector position is in what we call standard position. So over on the left-hand side, you see standard position. And what's to note about standard position is that the initial point gets moved to the origin. And that makes it nice and convenient for us to compare and make sure that vectors are equal in magnitude and in direction. So we call each one of the components, oftentimes we break apart a vector to describe it in terms of a horizontal component and a vertical component. So the horizontal component I'll label on the as the change of x, but the horizontal component, let's call that v1 here. So that's going to describe my change of x. So if I wanted to put something into component form, I would simply find the change in x. And then if I wanted to find the vertical component, I would find the change in y, similar to what we would do if we were finding slope. So that's called that v2. So component form is written usually as v1 comma v2 with these funny sharp looking brackets that you see here. And I will rewrite v1, v2 as change in x. So whatever your initial terminal points are, you're going to take the terminal point for x and the x value at the terminal point and subtract out the x value at the initial point. And then y2 minus y1. A unit vector is often referred to as something with a single unit of measure, or in other words, if I were to find the magnitude of a vector and found that it was equal to 1, this is called our unit vector. And later on in more advanced calculus, you'll see the use of the unit vector in certain formulas. A zero vector is a vector with no magnitude. So if you think about a vector with no magnitude, that means it's a single point. So there is no direction tied to it at all. Okay, so we're going to go through and complete this vector operation, which is also review for you. So given that you have two vectors written in component form, where the x, the horizontal component, is u1 for the first vector and v1 for the second vector, and the y component or horizontal component is u2 and v2 respectively of vector u and vector v, then we can perform a simple operation in order to do things like add two vectors. You probably learned it graphically in geometry as tail tip, or in physics as that as well. So it's much easier though if we can break down a vector and then put it into component form for us to perform these operations. So if I wanted to add two vectors, I would simply add the two x component and add the two y components. And similarly, we could do the same thing with the horizontal components for subtraction of two vectors. And then finally, another operation we can do is take a scalar and multiply it by an existing vector. And that's usually if we want to double the size of a vector, or if we want to cut it in half or change the size of it. So if we had a constant k on the outside of a vector written in component form, we can simply think of it as distributing the k to each one of the horizontal and vertical components. So k times x and k times y. On the next page, go ahead and flip to the next page, page 8. We'll find a few problems that are a review that involve us applying some of these vector operations. So for example, let's do v minus w. If we're going to do v minus w, that's simply taking the horizontal component and subtracting out the horizontal component for vector w. So for example, if you'd like to show your work on these, you can write vector v and subtract out vector w. So if we distribute the negative, or we think of it as 1 minus 4, we get negative 3 is going to be the new horizontal component of my vector, my resultant vector. Negative 2 minus 3 would be negative 5. And with part B, you see that this time we're going to distribute 3 to vector v first. So I'm going to do that and triple the horizontal and vertical component. So that's going to result is 3, negative 6. And now subtract out vector w, which is 4, 3. In doing so, we have 3 minus 4 is negative 1. And negative 6 minus my 3 is negative 9. Now the part C and part D, when I made these, I didn't make the double absolute value bars, but this is asking for the magnitude. So what I would like you guys to do is for part C, find negative v plus 2w first, and then find the magnitude. So go ahead and hit pause and then see if you can get to the answer that I have. So if we think about 7, 8 as the new vector after you first complete the negative, so you always want to do what's inside first. So distribute the negative to v and then double w, and then combine the two vectors to get 7, 8 is your new vector. If I ask then to find the magnitude of 7, 8, I would square the horizontal component, square the vertical component, because those are the legs of my triangle. So looking back on the next page, it would represent this and this that I'm squaring and basically applying Pythagorean theorem to get square root of 113. If you can try D and double check your work. Okay, 5, 1 is the new vector. And then if I find the, in this case, the magnitude first and then square it, I have the square root of 25 plus 1. And then it's telling me after I find the magnitude to square the whole thing, which results in undoing the square root. So my final answer, 26.